Thank you for, for the invitation. And it's really great to be here. And I'm very happy to open for Lorenz today. So I'll tell you some work that came out in the summer, part of the larger collaborations on trying to understand broadly what symmetries in quantum field theories are and how we should more properly understand them and do physics with them. So in the recent years, we've seen a huge explosion in generalization of what we want to call symmetries. And this is centered around the theme where we should think about symmetries in quantum systems as being implemented by topological operators. And this started with a rather nice story by Davide, Anton, Nadi, and Brane. So this perspective is, while this paper made it sharp, in a sense is always there at the back of our mind of how we want to think about symmetries. Intuitively, if we go back to quantum mechanics, we call a symmetry operator anything that commutes with the Hamiltonian, and this is preserved under RG flow. So in a very sharp sense, if we consider something in the Euclidean space, symmetries are objects that are preserved under small deformations, right? And this is what we intuitively want to think about as being topological. This has rather significant consequences when we think about selection rules in physics, when we try to construct effective field theories, RG flows. Importantly, anomalies are very powerful in controlling the IR phases of quantum systems. And if you have this rather broad notion of symmetry, it's always important to understand what does it mean for the broader Landau paradigm in trying to understand physics and quantum systems in general. So to put things on a little bit sharper, what do we mean by topological operators implement symmetries? So something that we're all familiar with, if you have an ordinary symmetry, which is what we learn all in school, you can measure the charge of an operator by surrounding it with some surface, which is codimension 1, and then integrating something like another current of sorts. So this allows you to measure the charge or the representation of the operator. The fact that such an operator, we can call it U, it depends on the surface that we inserted to compute the charge. The fact that it's topological actually follows from Noether's theorem. So the operator U depends on sigma in a topological way, meaning if I deform sigma, it doesn't change until it actually touches an operator. And in general, while you can start with Noether's theorem and actually show such an operator is topological, this perspective works in both implementing continuous and discrete symmetries, where we may not have a current directly to work with. Another important aspect of symmetry that we learned early on, if I take two symmetry operators and multiply them, I can label them by a group element. And when I multiply them, I get another operator, which is labeled by the group element, consistent with just the product of G1, G2, as demonstrated here. Now, the story, of course, in this review doesn't end here. Quantum systems can also have extended operators. These are typically charged with what we call in higher form symmetries. From this perspective, what it means is that you have operators that depend on higher codimension surfaces. Here, for example, dp minus 1. Such an operator can braid with some extended thing of p dimensions. Okay, so symmetry operator supported on a dp minus 1 dimension surface, which is U, can link non-trivially with p extended operator, which defines a p-form symmetry. And such a operator is what we typically call higher form symmetries, and are also part of the game when we think about this story. Now, this perspective has also other consequences. If we are to take this broader picture of topological operators, in general, the fusion rules of topological operators, if I take two of them and put them on top of each other, it's not necessary that I get a unique operator on the other side. In general, I cannot even assume that they will be labeled by some group and their products captured by group action. What we can generically expect is that if I take two operators and fuse them together, I should get some sum with some structure constant sitting in front. And one of the important implications of this more general fusion rule is that if I take an operator U and I multiply it by its conjugate, I shouldn't generically expect to get the identity operator. And this introduces the notion of non-invertible symmetry, right? Because it's an operator where you could put it, you can't undo it by multiplying with its conjugate. And one of the recent works is to sort of, so this thing might sound a little odd. For one, you should ask questions about unitarity in quantum field theory that we expect. But this is a question about what should be the representation of these objects in general. But we're already familiar with such a feature in lower dimensions. We have Verlinde lines. If you take the Ising model, the self-dual point of the Crémieux-Wanier duality, you have such operators which are non-invertible. The exciting things that happened recently is while these are well-studied and understood things in lower dimensions, in recent times, there's been an explosion that actually demonstrates these non-invertible symmetries that can exist in dimensions higher, in 4 dimensions and higher. In fact, this point was how you can construct such a thing was actually telegraphed in an earlier paper by Yuji. And then these 2 papers that came out a year and a half ago sort of had an explicit construction in 4 dimensions that actually start to show that these things can exist in simple bread and butter theories like QED or QCD that we used to think about a lot and play with all the time.
What does conjugate mean here? What is the meaning of conjugate?
Conjugate here will mean charge conjugation, for example. It'll be sharper later when I put it in another context. Okay, so since this story, there's been a huge explosion in the literature of many examples of these non-invertible symmetries being constructed with new methods, all sorts of fun and interesting generalizations. There's been some work trying to understand them in a sense in category theory, where all of these new results are really within the realm firmly of quantum field theory and using quantum field theory methods. There is a huge set of people that I should cite here, but this is a 30-minute talk, so please forgive me if I don't mention your work. Okay, so my interest, at least being trained in string theory and holography, is we have this wonderful thing called ADS-CFT, where we can think about quantum field theories as actually coming from geometry. So from this perspective, what we would like to understand is, suppose I give you some operator that I insert in some boundary field theory. Here, this operator could be extended in a suitable directions. There are symmetry topological operators that I could surround this to measure the charge, or more specifically, its representation. What happens to this thing when I drop it in the bulk? What is the bulk origin of these symmetry operators, and how should we understand them and construct them? Okay, so this is the main question of interest in this talk. So there are 2 parts to this question, right? So we have 2 ways we think about ADS-CFT. There is a bottom-up picture where I give you some effective theory in ADS, and from there I should reconstruct operators, I should reconstruct everything. There is one question, which is, how do I understand the origin of topological operators in holography from the bulk? Just from a bottom-up, given some effective theory, how do I do that? And then there's also a top-down, because we would like to believe that holography is a feature of string theory. We obtain explicit solutions and explicit duality that we construct in string theory. So from string theory, what sort of stringy states should capture these non-invertible symmetries, or broadly topological operators, and what should be the rules of those objects? Of course, an important thing to understand, if I take a topological operator and I drop it in the bulk, I should not expect it to be topological. Generically, it should be some dynamical operator. And I should understand also the dynamics of such an operator and what implications it should mean for this. So to just give you the answer to both of these things, so from a bottom-up point of view, you can actually argue and show the existence of these operators by studying Gauss law constraints of bulk gauge theories. And then from a top-down point of view, if you study D-branes reduced suitably on X, they can also capture these operators when pushed to the boundary, give you these topological operators. So let's see how this works. First, in the Gauss law constraint. So the work here is the start of our paper, and it was heavily motivated by earlier work of Belov and Moore. So suppose we have some U1 P-form symmetry with some gauge transformation in the bulk. So we're supposed to think about global symmetries in the boundary as coming from gauge symmetries in the bulk. So let's consider a U1 P-form symmetry. One thing that we know is that if you consider the quantization of such a gauge theory, the Hamiltonian quantization of gauge theories, because of a gauge symmetry, there is a Gauss law constraint that exists. Okay, so if I take some time slicing of my space-time and I quantize the theory, there is a Gauss law constraint because the action will not depend on the time derivative of some mode, namely the one that's a long time. So classically, we implement such a constraint by saying that the variation of the Lagrangian with respect to AT, where AT is a component of the gauge field along the time direction, we set it to 0 as a constraint. This is like del dot E equal to 0 in Maxwell theory. However, in the quantum theory, this is an operator. We cannot just set it to 0, but it cannot act in any interesting way on physical states. However, what it does is that it generates gauge transformation, meaning a particular gauge transformation, meaning if I take a slice at some constant time, then such a slice you can almost think of as preparing some state of your system in Euclidean space. Then the Gauss law, what it actually does, it generates gauge transformation along that slice. Okay. So while classically we throw it away, quantum mechanically it is quite interesting. It actually generates gauge transformation along constant slices of time evolution. So this perspective now is quite useful because now it tells you that in the bulk, if we consider the bulk by doing some quantization where we take the time direction to be the radial direction, then the Gauss law constraint allows us to talk about generation of gauge transformation along some slice, some constant radial slice. And in fact, an observation is that the Gauss law is going to be a closed object. You can see this from more general principles. So there's a notion of a phase charge, which is the antiderivative of the Gauss law. Then the transformation it will implement some operator U, which acts on MT, where I can just move the derivative on the side formally. Interestingly enough now, if I consider a specific class of gauge transformation, singular gauge transformation, which localize on some codimension P surface, then such a singular gauge transformation naturally generate operators U, which generate gauge transformations on MT, and these operators are going to depend on some choice of a surface. So we can identify, for example, this bulk operator which generates gauge transformation with the object that I get when I drop it inside the spacetime. Okay? So this is not the end of the story. Here I was a little fast. Of course, when I'm moving derivatives here, I need to be careful and in defining such an operator, whether P is actually a well-defined object. And in general, it's not going to be, and we'll see examples of this. And what you have to do to fix it in this perspective is usually you add some extra mode that live on this surface. And when you consider such a mode that live on the surface, then you can have a well-defined term which you then integrate over. This important feature is going to lead us to actually being able to describe non-invertible symmetries in the bulk, or more specifically, non-invertible base charge. So from the other perspective of the branes, we can also ask how this comes about. So the bulk operator UB is going to be captured by some brane wrapping internal manifolds. The branes are going to be required to be stable, but not necessarily calibrated in the sense of supersymmetry. And the branes are going to be extended along some slice MT with constant radius. An important consequence of this, to have that the branes are parallel to the boundary, is that there is an effective tension that gets generated in front of the kinetic term, or the dBi part of the brane. So there is a kinetic term and there is a Wessel-Zumino term. And the effective tension here, it gets large when you approach the boundary. So the effect of this is to freeze the fluctuations on the brane. So as you push the brane to the boundary, the only term that survives is the Wessel-Zumino term, and it becomes a topological operator. Okay, so this is how the branes themselves become a topological as you push them to the boundary. So the leftover Wessel-Zumino term is the thing that's going to capture your topological theory that defines the operator. Then there's the question of how to understand fusion from the perspective of the branes here. So the fusion rules of the topological operators are going to be realized in some way by the brane dynamics. In particular, to sort of telegraph some important results here, is if you consider U and its conjugate, if I associate a specific brane to U, then this is a dP and an anti-dP brane fusion. But this, of course, we know such a fusion is not necessarily just an identity operator. It's going to be some sum of lower branes, right? So this is how we can see from a brane perspective that you should expect these non-invertible symmetries. Okay, so any questions? So I'll work out an example to demonstrate some of these things. Okay, so as an example, let's consider one theory that we've all have come across at some point, n equal to 1 super-Yang theory. So in holography, there is a way to describe this model. If we consider type 2b on ADS5 times T11, where we turn on m units of F3 flux with n units of F5. So famously, this picture is dual to the duality cascade, which was studied by Klebanov-Straussler and Klebanov-Salin. When n multiply m, the cascade will actually end at an n equal to 1 super-Yang theory. Okay? So this type 2b setup here knows something then about this n equal to 1 super-Yang theory. In particular, the symmetry structure and the property that is shown. The gauge theory, if you just take n equal to super-Yang mills, admits a discrete global symmetry, a Z2M zero-form symmetry and a ZM one-form symmetry. The zero-form symmetry is coming from the U1R symmetry, which gets broken down by an ABJ anomaly. And the discrete one-form symmetry acts on Wilson lines. Okay? So a consequence of the ABJ anomaly, a leftover of the ABJ anomaly, is that there's a mixed Tufte anomaly between these two symmetries, Z2M and Z1. And this mixed Tufte anomaly is usually written in this way. A1 is a discrete background field associated to the Z1, to the zero-form symmetry, and B2 is a discrete background two-form associated to the one-form symmetry. So this is a Pontryagin eigendual. So here, this is a product of object in cohomology. So we use the cup product. But formally, when you see this thing, you should just think of A wedge B squared. Okay? So the reason why we don't write A wedge B squared, because A wedge B squared, if you treat those gauge fields as being continuous, is not well defined, is not gauge invariant. But products of cohomology elements are, and this is well behaved. Okay. So one of the important consequences of n equal to 1 super Yang-Mills is that you have this discrete one-form symmetry, and you have an anomaly, you can gauge it. So gauging this is the gauging of the center symmetry of the gauge group. So gauging the one-form symmetry nominally would break the zero-form symmetry. However, it turns out this can be recovered in a clever way. If you take the topological operator that you had, which was associated to the zero-form symmetry, and you stack on top of it a 3D U1 level M Chern-Simons theory, then you recover a new topological operator, which itself becomes non-invertible, and we'll see the explicit example later. And when you do this, the gauge group now is P SUM, not SUM anymore, and you've divided out with the center symmetry. Okay? But the PSUM theory of n equals 1 super Yang-Mills have non-invertible symmetry, and that is the upshot here. And we will see this arise explicitly in holography. Okay, so what is the example here? So what we want to do, as I said, there's two pictures. There is a bottom up and there is a top down. So let's briefly talk about the bottom up. So the reduction of type 2b on T11 with m units of flux will give you some effective supergravity theory. I will write the action in this way. There's two parts. There's the kinetic part, and then there's the topological part. The fields of the theory can be captured by these 5 potentials, a 2-form, two 3 forms, and a 1 form. These will satisfy some Bianchi identity, which is inherited from the Bianchi identities of upstairs. And to express, so this part is the topological part of the action. It's usually expressed in a dimension higher via inflow, at least defined appropriately in a dimension higher by inflow, and then I need to be able to pull out a derivative to define some 5D topological action, or some 5D Chern-Simons theory. So to do so, I solve these Bianchi identities, but in solving them, I insist the following way. The fields that appear, the local fields that appear, are going to be all globally defined fields. And in particular, I will peel out these terms, which themselves are going to be object in cohomology. So the pieces, so G2B here, for example, is going to be a closed form, and it's part of the solution of the Bianchi identity. And technically what it does is encoding the cohomological data associated to B2. So in particular here, if you look at this term, here, this is a Stuckelberg coupling of a 2-form with a 1-form. So this 2-form defines a 1-form gauge symmetry. The Stuckelberg coupling breaks that 1-form gauge symmetry, and it breaks it down to a ZM, 1-form symmetry. This is how the supergravity knows about this global symmetry. Similarly, if I look at this term here, there is a U1 gauge field, which had its origin from the R symmetry, but it has a Stuckelberg coupling with an axion, so this also breaks this U1 to a discrete Z2M zero-form symmetry. Okay? So in doing so, A1 is going to be valued in some discrete group by the Stuckelberg mechanism, and B2 is also valued in some discrete group by the Stuckelberg mechanism. So I peel out that cohomological data out to keep track of it as a separate entity. because it's more convenient to do so, and I will not run into issues of gauge invariance in thinking about continuous fields. So the effective action, then the 5D action that gets constructed is this. So you have a BF term, which describes B2 as a one-form symmetry, and you have another one which describes a zero-form symmetry. Then you have this term here, which exactly captures the anomaly. Yes? You can take W5 to be ADS5, but since this is an effective supergravity, you don't need to. You can consider it actually this to be a hard boundary, and it's also consistent. Thank you. So here, in reducing the supergravity and being careful to keep track of the cohomological data, we exactly recover the anomaly of these discrete symmetries, right? So we do not get things that are like ABB, which is inconsistent and not gauge invariant, but you actually get a product which involves the cohomological data associated to these symmetries. So now, with this, we can proceed by computing the Gauss law. In particular, we will compute the Gauss law associated to A1, which is the U1 gauge field. But remember, this U1 gauge field is Stuckelberg down to a Z2M discrete symmetry. So the generator we would compute by this would be a generator for this discrete symmetry.
Question?
Go ahead.
Was it important that you had supergravity here? Will basically the same analysis extend if I do a 5D QST coupled, almost basically with a boundary coupled to n plus 1
No, that's not. So here I'm doing supergravity because this is a context which I want to understand this thing. But in fact, this theory that I construct is more broadly what we call symmetry, SymTFT, symmetry topological thing. And this is a way of describing SymTFTs using continuous data and cohomological data. So it wasn't particularly important to do supergravity, but since I'm in the supergravity regime, supergravity should be able to obtain this. So the weird thing is that it was unclear. So there are papers out there where they write supergravity actions, but there's various pieces that are ill-defined. But this is a procedure which makes everything well-behaved. Good. So we can compute the Gauss law. There are two terms. There is a term that involves C3. Oh, so C3 goes with A1. Oh, there's one. Let me see. There's one piece that I. So here, when I computed the effective action, notice that there is this BF term, which gives you a discrete Zn symmetry. But I kept this G2, its kinetic term, which is a Stuckelberg, which is a Zm symmetry. So actually, supergravity would pick the discrete symmetry, the GCD of n and m. But here, I'm in a context where n is a product of m, so the discrete symmetry is actually G. Whereas here, I have a C3. This C3 is obtained by dualizing C0 over here. So that's what I get over there. So when I compute the Gauss law associated to A1, I get this expression. So this object, as you can see, the Gauss law itself is globally well defined, but I cannot pull out a derivative to define a phase charge exactly because of this term. Okay? And G2B is a part of a bulk field and that I have to sum over in a path integral. So, however, this expression here, you can note that if you look at the exponential of this square, you can rewrite it by introducing a field A on my spacetime, a local field, and then when I integrate it, it becomes a Chern-Simons theory coupled to this G2. So I can rewrite this object here with respect to this object. So this then allows me to pull a derivative out from this Gauss law and define my operator in this way. So I have this C3 potential, which is expected, but then I have it that the topological operator necessarily has a 3D level, a U1 level M Chern-Simons that lives on it. And this is a derivation from the supergravity. Okay? And similarly, you can just read off, you can just take this operator and multiply it with its conjugate. So you have an I here, and then you get something that is non-trivial, and this non-trivial thing will have an interpretation in a moment. Go ahead.
You know, we put it here at W5 and non-trivial cohomology. So if I
Yes.
take non-compact ADS5, this would be not be there.
Yes. I mean, but the assumption always is that, you know, we're keeping track of discrete background fields for gauge theory, so we put it in a background that has non-trivial cohomology. So in the dual CFT, so I have a couple more minutes to just finish, what happens in the dual CFT, in order to in ADS CFT, I have to fix a boundary condition to pick a symmetry structure. So if I fix A1 and G2B at the boundary and sum over the other fields, then the dual theory will have this discrete symmetry where the boundary values of A1 and G2 become background fields for this gauge theory, for this global symmetry. So in this case, G2B is just a constant, and you can actually integrate out A. And then when you integrate out A, you just get this operator, and you just get some constant which you can throw away. So the actual bulk operator that you derive from ADS-CFT for this thing is just integral of C3, which is an invertible object. So this is how you see that although the bulk phase charge is not invertible, when you push it to the boundary for the Super-Yang-Mills, for the SUM theory, it actually becomes invertible. On the other hand, if I want to consider the PSUM theory, I fix A1, but I need to sum over G2B. So in this case, I am not allowed to integrate. So actually in this case, you get the zero form symmetry. You also have a discrete magnetic one form symmetry, but that's not important here. So in this case, I'm not allowed to integrate out A, and G2B is dynamical, and the operator near the boundary is the full thing that I've derived in the bulk. And it's indeed non-invertible, and it reproduces the non-invertible symmetry of the PSUM Super-Yang theory. So finally, to explain how the branes come in now. So now this is my operator, and the claim is it also can be derived from a brane setup. And this picture is, you can read this off by looking at the supergravity field and chasing where they come from in string theory. So the C3 potential here, before the anomaly was on, came from reducing F7, which is dual to F3 on the sphere. So this is a coupling which involves D5 brane. So this operator, you can actually then go ahead and check. If you take the Wess-Zumino coupling of the probe M5 brane in ADS5 times T11 with M units of flux that you reduce on the sphere, you exactly recover this operator, where here, the gauge field, which in the low energy limit appeared as an integration trick, is a field, corresponds exactly to the gauge field that lives on the brane. So you can very clearly see where this thing comes from. And you can also then check that the fusion rule that you had here, which gave you some complicated object here, the terms on the right-hand side, you can reconstruct by looking at D3 branes that wrap this M2 and then extend it on the sphere inside the tree sphere. Then you can check this works. So this exactly is consistent with the tachyon condensate picture where you annihilate a brane and an anti-brane, and then you get lower branes. Finally, you can then start to just play and ask what are the various fusion rules that you can obtain from the brane picture. If you take the operator with itself, this corresponds to a D5 with another D5. So this, you can, if you compute the answer here, is exactly equivalent to taking a D7 brane and reduce it on the T11. So this is exactly a case where the fusion rule here is being realized by Meyer's effect, where you take 7 branes with 2 units of world volume flux. Okay? So to conclude, so we described how to realize various novel aspects of generalized symmetries and topological symmetry in holography. The holographic prescription here is an honest-to-God derivation, right? It's you follow the rules of holography and then you actually obtain these things. So in principle, this is something we could have known long ago. More excitingly, since we were trying to understand all of these symmetries, there's a lot of new ideas here and there. This work here, it just shows you that if we do start from string theory in holography, we can systematically explore these things and see where they are and try to understand what they do. And ultimately, we would like to understand what new things they teach us in physics. And I hope, hopefully, this work is the start of doing that.
Thanks, Ibo. We have some time for discussion or questions. So please,
Go ahead.
By the way, Eric, it seems like Zoom picks up even if people don't have mic. Maybe we should have.
I wanted to ask if there's an interesting action of SO2Z, meaning magnetic version of these operators, NS5 instead of D5 Branes, and so on.
Yes, this should exist. I haven't explored it typically yet. So one place where it becomes important is when you try. Another way you can obtain these operators is as duality defects, as self-dual points. So there they become important and critical. So if I'm trying to think about, some operators coming from the 7 brane, it becomes critical. There was a paper recently by Heckman where he tries to explore this, and there was actually some work by my collaborators that also tried to explore this.
I'm wondering what happens when you have non-trivial space-time topology in the bulk, like Euclidean wormholes or that kind of thing.
Yes. So good. You're the right person to ask this question. Right. So in that case, these things are broken, as you know. You shouldn't have topological operators when you have wormholes. There was a nice paper by Yiming and Henry Lin where they tried to do this, and there was subsequent follow-up. In what sense, in a very sharp way, how you should lose them, at least I don't understand yet, and this is something that I'm thinking about, so we can discuss. But they shouldn't be there. They should be broken. Yeah.
I'm a little confused about how your pro-Brane construction works.
Okay.
So the claim that you made earlier in the talk is you want to freeze out the DBI term. Mm-hmm. You have a Brane that's parallel to the boundary way off. But then the D5, it still has to be the case that the world volume scalars are really, they're sitting at their minimum, where the Brane is sitting out at some large R. And
okay.
For the D5 Brane example that usually if you look at D3 Branes in ADS 5 times S5, the way that happens is because there's a force balance between DBI and Westonino. But for the D5 Branes that you said that there's...
Good. So the statement that I made is the Branes are not necessarily calibrated. So the statement that you made is a condition of where the Branes are supersymmetric and they balance each other. But here, I'm just computing these operators, and I'm asking what happens. So certainly, when I take this topological operator and let it drop, it's a dynamical mass inside. It doesn't have to stabilize anywhere, but it's just the fact that it exists in the bulk as this thing. The statement about the tension is just that whatever happens to this dynamical object, when I approach the boundary very, very close, it better remember its topological nature. It better behave like a topological object. And what that means, a necessary condition for that is that all the local fluctuations should freeze out. So the tension argument is to just tell you why those local fluctuations freeze out when you approach the boundary, because the effective tension grows with R. And this is the case for every Brane. But deep in the bulk, this is a dynamical object.
Thank you.
I was wondering if there's a unified perspective of the following. Some of the global symmetries in boundary field theories in areas, I think of as coming from just geometry, like the R symmetry just comes from the SO6, or in this case, the U1R symmetry coming from the Reed vector of T11. But some of these other symmetries come, as you said, from Branes wrapping cycles, or from, in the topological case, from their existence of non-trivial cohomology, post-compactification.
Good. So most interesting symmetries in ADS CFT do not come from isometries. Isometries are usually very simple and boring.
Right.
They come from because you have a manifold with very exciting internal topology, and then you can have branes that wrap to cycles which become small and give you light fluctuations in the external things. So there's two answers to this question. One is, if I'm working from the point of view of just the effective ADS theory, so I and a few others actually just worked out the general anomaly polynomial theory that you would get that would capture all of that. And indeed, in those cases, so they become very big and very non-trivial. If I give you such a theory, I can run my Gauss law constraint and derive these symmetry operators in those cases. And indeed, this is a straightforward thing to do. But in the same way that if I look at those cycles that generate those symmetries, there are dual cycles of those which I can wrap branes. And those dual things are going to be the thing that's going to generate these symmetries from the bulk. Yes, indeed.
So your perspective is basically that if you could write down the most general anomaly polynomial in, say, M6, then you'll be done, including all the...
Yeah, so this is done. I have several papers where I worked this out. Actually, in fact, some of the symmetries here that we see are coming from, the flux. Mm-hmm. They're not all coming, even in this very simple case.
Great, thanks.
So sometimes the internal manifold has, like when you deal with orbitals, you have these like torsion cycles. Do you have any understanding of the discrete symmetries that come from the wrap branes there?
That's right. So torsion cycle, you should just think of them very similarly as cohomological cycles. So cycles that are free elements, they just give you continuous symmetries. The torsion cycle gives you discrete symmetries, and you can compute the anomaly polynomial to that. And the way you do it is you use the language of differential cohomology, so we know how to do that. And then you can compute what would be appropriately called the symmetry TFT associated to the field theory. Yes.
Eric, do we have anything on Zoom?
Okay, thank you.
Okay, let's thank you again.